Now, let me just start putting some annotations there, which is A. Let's put this node here A, and this node here is B. Yep. So we have, if you look at the sinusoidal waveform, as you know, you'll have positive cycles and negative cycles. Just putting two of them, but it repeats. Yeah. Now, in the positive cycle here, you can assume that this is A is positive and B will be a negative polarity, or B can be assumed to be grounded. So one way you can very easily analyze the circuit is to assume B to be always at 0 volts. Like I've also shown you in the fundamental part last time when we looked at a circuit where you had batteries, remember? So we said let's ground this terminal of your voltage supply, and then the what happens on top is going to be your voltage. Yeah. So for example, if you take any point on this positive half cycle, let's say this is plus 10, this is going to be 0, and A will be a plus 10. So you have 10 volts across it. If you are 20, this is still 0, and this is going to be at plus 20, and so on. So during the positive half cycle there, your point A would be at a positive polarity, positive potential. So if you look at a circuit, if that's positive, your diode is forward biased. Yeah, it's forward biased, and it's going to, current is going to flow in this direction. Yep, this is what's going to happen. Okay. Okay, so it means when your input voltage is in the positive half cycle, you expect your diode to be forward biased. Now, ideal diode, you can just replace it by a short circuit, like I said. Okay, so that's your ideal diode. In the positive half cycle, you can assume this to be a short circuit. So current simply flows here, and you can find your V naught is simply equal to your supply. So if you had to plot a graph now, just plot it down. So you could be plotting these graphs in your copybook as you go along. So you can draw the input waveform. We typically do that. And then what are we trying to do here? We're trying to, I'm just going to put that as a different colored line, this one here. So we want to see what waveform we'll get for your input, for your output, sorry. And see where your output is connected. It's across the 75 ohm resistor. Now we are assuming ideal diode for the time being. Then afterwards we'll see if it was actually a real diode, what are we going to obtain? Okay. Now, if I just 1 minute, yeah. So actually we had our diode here, and just draw back the other diode circuit so we can come back to it, and just take this part only. Yeah. Okay. And just come back here. So I just want to keep the original circuit so that you can see what changes I'm doing. Just a second. Yeah. So this was our original circuit. Yep, original circuit is here. What did we say now in the positive half cycle? Since your A and your B here, so A is positive, so this diode is forward biased, you can replace it by a short circuit like we just seen. Your circuit becomes very simple now. You just have your voltage, which is being set across your load. So what V naught would be, it will simply be your applied input. There's no drop here. Yep. So it means you would just be copying this section here. So in the positive half cycle, what would you get at your output would simply be your input, because this is what's appearing across your output. This one here. Okay. So this is what you would expect to get. So this one, what I'm drawing here is V out. So this is your output. V out. This is V out. I'm drawing V out. So what we've seen is when you are in the positive half cycle, the diode can be represented as a short circuit. So you can just forget about the diode basically. And the voltage you apply here would simply be read across the 75 ohm resistor, which is nothing but V naught. This is why for the positive half cycle, you will get your input. That's very simple. Now, what happens in the negative half cycle now? So based on what I've just said to you, in a negative half cycle, you can replace your diode by an open circuit. If I just go back to what we said here. Yep. So in the forward mode, short circuit, we've done that. In the reverse mode, it can be represented as an open circuit. Why? Let me explain this again. In the forward mode, in the forward mode, it's allowing current to flow. But what allows the current to flow is a short circuit. In the reverse mode, it's blocking current. If you look at the profile, a very small current flows, ideally no current. So what actually prevents the current from flowing is an open circuit. That's very simple. So this is why here, when you are in a negative half cycle, what is going to happen to A now and B? So B is maintained at 0 volts. You can assume your B is at 0 volts. Yep. So your A is going to be, for example, if your voltage applied is minus 10 volts, your A is going to be at minus 10 volts. If it is minus 20, your A is going to be at minus 20 volts, so that across the supply you get your minus 20. Now, if you have 0 volts here, and let me write it down here, this for the peak value, you have minus 20 volts. This is special. This is just one point on your curve. So if you have a situation like this, yep, let's put it here actually, because that's your. Let's put this 2 here. So you have a situation like this where your A and B are like this. Yeah. Okay. So if you have a situation like this, you have minus 20 volts here and 0 volts here. Definitely, this is more positive. So 0 volts is higher potential at minus 20. So current will try to start flowing like this now, and it cannot, because this diode is reverse biased. Reverse biased diode means we can just open circuit it. It means now it's going to be like this. Yep. So if you want, you can draw a switch like this, but open circuit is enough just to show it is open. So your diagram is like this. So in reverse mode now, in the negative half cycles, your diode is going to be represented as an open circuit. No current is flowing now. So if you are to apply Kirchhoff's voltage law, if you go around this loop, the sum of voltage has to be equal to minus 20. Since no current is flowing through your 70 or 75 ohm resistor, there's no drop. So V naught is 0. The full voltage that you have here will simply occur across the terminals of a switch here. So in a way, your full negative 20 volts in that case for the negative segment, any voltage you have is going to appear across the diode. So in a way, V naught is going to be 0. So in this segment there, if I just draw it in different color, put it green, bit more. So in this segment there, you will have 0 volts because there's no current flowing through your resistor. And simply you is going to repeat that now. This is what you would expect to get as the output waveform. So this is what we expect to get. So what have the diode done? It has simply kept all your positive half cycle and simply suppressed all your negative half cycle. This is known as a half-wave rectifier. Yep, it has maintained only the positive half cycles, and the negative half cycles have been nullified. Consider a real diode in the forward mode. So if you just go back to what we did, so this waveform will be very similar to what you would get with a real diode, except for some differences. Let me just show the differences to you. First difference is when you are in the positive half cycle, a real diode would have a voltage drop of 0.7 volts across it for silicon and 0.3 for germanium. If in a question you're not given any information on what type of diode it is, you can assume it to be silicon. So you can assume 0.7 volts. So in the forward mode, you would put a simple short circuit like this, that's fine, but you would have to know that you would have a drop of plus 0.7 volts across it because it is in forward mode. So what would happen here? Your graph will simply shift down by 0.7. Yep. So you won't get a peak value of 20. In the ideal diode, this value is 20 because we assume there's no drop across your diode. In a real diode, simply you would have a 0.7 volts drop. So you have to subtract 0.7 to get V naught. So this peak value here would be 19.3 volts. That's going to be the difference. Yep, that's the only difference that you have. And your graph is going to start here. So what basically you would do, you're going just to shift this graph down by 0.7, but whatever comes negative will be suppressed because we say there are no possibilities for negative here. Yeah, so this graph will simply shift down by 0.7 volts. That's the only difference. Now, in this question, there's no mention here of what resistance you have in the forward direction. We know it's a very small value, like 10 ohms. If no information is given to you, you can neglect it. If that information is given, what should you do? So you would going to add not only a drop here, you would also add a resistance to it, and then you will apply the voltage divider to be able to get your the voltage that you actually get across V naught. but typically this resistance is ignored. So you would have just to consider 0.7 volts drop, which is always there for a real diode, whereas the resistance is not typically reported. So you can ignore about the internal resistance of a diode. You can just consider the drop is there. So the fundamental difference between an ideal diode and a real diode is that 0.7 volts, which is required for a silicon diode for conduction to occur, and it's a drop which is there always when the diode is forward biased. In reverse bias mode, reverse bias mode, you will simply assume that it is exactly like this. So you will get 0. You have a very small leakage current that's in microampere, so that's not going to make big difference. So this is going to still be like this. Yep. You might have a very slight difference, but that's not something you're going to worry about because we know the leakage current is in microampere, so that's not very important. Is someone trying to join now? Okay, so if I just go back to your slides now, let's read the question. So actually, so that has a resistance. So can you see 75 ohm there? So if it is given, you have to factor it in. Yep, so that's important. If it is provided there, the diode has a resistance of 25 ohms. So you would have to put 25 ohms there in the forward mode. That's important. Okay, and if it is mentioned germanium, the voltage drop would be 0.3 volts instead of 0.7 volts. So these are important information that you need to consider. So the ideal one, we've done it, what I've drawn. The real one, you're going to have a 0.3 volts across the across the diode. Yep, you have 0.3 volts at least for it to start conducting. And when it conducts, you have to factor in the 25 ohms. Now let's do that. I'm going to show you what to do with the 25 ohms. So if in the forward mode here, let me just remove this. It's no more now a short circuit because it is now a resistance. I'm going to represent the resistance as a box like this now. Yep, so 25 ohms resistance. This is a real diode. Okay, so let's put our 25 ohms now. So this is 25 ohms. This is your actual real diode, how it's going to be. Now, if you want to measure V naught now, so first thing is this voltage will not start picking up immediately here. You would need to exceed 0.3 volts. So how you do that? 0.3 volts is very less, but if you have to draw it, you have to draw a line like this. I'm going to draw that in orange. So you have to draw a 0.3 volts line like this. Yep, it's only when you exceed that, so you have a small segment there where you have 0. So because it's going to be not conducting at this point, so this doesn't start straight away like this. It will have a small region where it's flat, and then it starts picking up. Now, when it picks up, what is V naught? You will apply voltage divider rule now. Yep. So remember, we are not talking of a negative voltage. This is in the forward mode, so this would have any value. So what is V naught in this case? Let's write an expression. Your V naught would be equal to, this is your voltage divider, so it's 75 divided by 75 plus 25, 100 times the in. So you will not have the full voltage, like we assume in the ideal case that the full voltage of your input is appearing across 75 for the ideal case. For the real case, it's only 3/4 of it because you have a drop across the diode as well. Yep. So you would take this one. I give an example. Let's say when the input is 20 volts. So your V out, so this is a peak value. Your V out would be 3/4 of 20. So you have only 15 volts. Yep. Because you have a resistance now in the diode, it's going to have a drop. So the remaining 5 volts that you find there would be appearing across this diode because it has a resistance. Yep. So two implications of real diode. First, you need to have at least 0.3 volts to start conducting. So you have a small segment there where it's going to be flat. So then your graph will start picking up somewhere there. It will not go to 20 volts. It will go only to 15 volts and then come down here. And when it goes again below this 0.73, it's going to become 0. And then it's going to be a small flat there. When it is reverse mode, it is exactly what you're seeing there. Any question on that? Is it clear how we model a real diode and an ideal diode? Okay, if there's any question, you stop me and you can ask. I will explain again. Okay. So let's continue. So this question there, we've answered it mostly, but only one part we have not answered is calculate the peak current in each case. Okay, now the peak current will of course flow when you have the peak voltage. Yep, or you have a peak voltage. Let's try to calculate the peak current in the ideal case first. Yep. So when you are in the ideal case, we've said this can be represented when it is short-circuited, sorry, when it is reverse mode, this is going to be an open circuit. Yep. So then no current flows. So there's no issue of peak current in the reverse mode because no current flows. So you will have a peak current only when it's forward mode. Yeah, when it actually is a short circuit or is a resistor. So let's go back to paint. And I'm just going to just cut this and put it aside. So we're going to use that again. So this is the ideal one. I'm just going to cut this. So we'll do that in a few minutes. So let's look at the ideal one first. Then we're going to come to the real one. Okay, so that's the case. That's the situation. Yep. So what did we say? Your peak value of V naught is going to be plus 20 volts. That's going to be the peak value of your input. Now, since you don't have any drop, be it 0.3 volts or any drop because of the resistance, the full 20 volts will appear across V naught. So what is peak current is simply, so peak current here would simply be equal to your peak voltage divided by 75. Yep, so this is going to be your peak current if it's an ideal case. Now, when we talk of the real case, remember what did we say? We have to replace this now by your 25 volts. So you would expect that now the current to be less because you have additional resistance in the circuit. You would expect this to be less. Okay. Now, if you want to calculate the peak current in this case here, if I do it in green, so peak current. So the output voltage, you can do it by output voltage, or you can just take 20 divide by the total resistance now is 100. Yep. So you can just do it like this. So the peak applied voltage here is actually 20 volts, but it doesn't appear only across the 25, it appears across both. So you can just add these two, you get 100 ohms, and then take 20 divided by 100. Yep. So this is your peak current. Okay. So I hope it's fine. Yep. So you can get your peak current. It's quite close in value if you just compute these two, but you can see in the actual case you do have less peak current because you are including some resistance in your circuit. So we are left only with the half positive cycles because we know in one half of the waveforms the diode is forward biased. This is where it's going to be behaving more or less like a short circuit or as a very low resistance. So current can flow across your 75 ohm resistor, but in reverse mode now, your diode is not allowing any current to flow or a very small leakage current. So basically, no current is flowing through the 75 ohm resistor using Ohm's law, V is equal to IR. If no current flows, V naught is 0. This is why we've got that. Okay. So this completes the first section of this first lecture, short lecture series, where we introduced semiconductor physics. Then we've introduced the P junction, the N junction, and then the PN junction diode. Yep. And then from there, we've got the diode, and we've more or less understood a real diode, what it is, and an ideal diode. We've taken one example.